Welcome to Physics Fundamentals. Okay, those are loaded. Go ahead and do our review of Chapter 21. So Chapter 21 was about induction. Okay, well, let's give a little reminder. There's some between electric fields or electricity or electric currents and magnetic fields. Sometimes seen in magnets. What are give me an example of this connection. Okay, current moving through a wire generates a magnetic field. That the current magnetic fields are related. So current moving through a wire generates a magnetic field. That was actually 2 chapters ago. We talked about that. We talked about Oersted, and he had a wire and current flowing through it. Okay, so there's some kind of connection that if there was a chain magnetic field, that we could create an EMF. Okay, so let me be a little bit more specific than that. Changing the magnetic flux induces an electromotive force or EMF or voltage, which then of course leads to current. Okay, we talked about charges, moving charges are affected by magnetic fields. Right? Magnetic field lines, charges will either go around it, gyrate around them, or travel along them parallel. The combination of those is that they will spiral along magnetic field lines. Okay, that's pretty good. So the key thing that's happening here is that we seem to have this situation where another way of saying current is moving charges, and these moving charges you might call something like a changing electric fields. So when we have electric fields generate magnetic fields, and changing magnetic fields through changing the magnetic flux generate electric fields. So there's this beautiful symmetry in how electric fields and magnetic fields work together. Okay, and that's an earlier question. Induction is new here. Induction is this idea that that when the magnetic flux, that we can create a new, we induce a current, induces a current. Technically, it induces an EMF, it creates an EMF, but then that manifests itself in the form of a current. And so we found that if we take magnets, no, let's do it this way. If we take wires and change these wires back and forth, the wires will, in the presence of magnets, the magnetic field the magnetic field from the magnets will create effects on the current on the. We also saw that if we take magnets and move them around, we can change the magnetic flux in a loop, in a wire loop, which can create a. Okay, so one of the above is an electric generator, and the other is an electric motor. Which one is which? And this is basically why electricity works for us. Why do you have wires running to your house, carrying electric energy with them? Because you can take that electric energy and turn it into motion. So one of these will one, let's call this 2, and this is motion creates electricity. And this one is body creates. Okay, and Joy is right. Number 2, the electric generator, and number 1 is the electric motor. Okay, notice that if you take wires and you put magnets next to them, then the magnetic fields want to push on the wires. And so the actual setup of an electric motor is you get wires and you put them in loops, and you get magnets and they push on the wires, and then you push on the wire, and then as it comes over to this magnet, you have a bunch of magnets and a bunch of wires, and you actually send the current through back and forth, and as it's and you do it at just such a rate so that it's pushed this way, and then it's pulled this way, and then pushed, and then pulled, and then pushed, and pulled, in such a way that it's coherent, and then it rotates. That's an electric motor. You can take electricity and turn it into motion, because electricity in the presence of magnets creates a force, a push or a pull. Similarly, you can, by induction, you can take magnets and move the generator. Okay, this is why, and we talked about a little bit, this is why electricity can be turned into motion. In particular, the way that you set up an electric motor, it's easiest to create circular motion. Motion, you get these wire loops to move around in circles. Once you create circular motion, ways of turning that into linear motion, wheels, for example. So you can, you can create motion. And the generator is the other way around. With motion, you can create electricity. And so we have created in our society a system where somewhere else, someone makes something big and heavy move. Maybe in a hydroelectric dam, someone makes a move. by putting water through the dam. And then that motion is turned into electricity, which is then carried to our homes into motion when we get here at a much smaller time. You know, you turn on your air conditioning, which takes electric energy to spin a fan. It takes that motion and pumps water. It takes that motion and does all these kinds of things with it, pushes air around, right? And electricity can create motion between magnetic and electromagnetic waves. And how this will work. And this turns out to be a really just stunning a method of using physics to understand and then really having a basic understanding turn into some amazing ability to interpret the universe around. So the first thing that happened is that, you know, some of these rules about, okay, we've talked about Ampere's law, which is able to talk about how much, you know, inducing electricity. We've talked about Gauss's law, about how charges and electric fields are related, and all these things. And there was a British scientist named James Clerk Maxwell who kind of saw all these laws and saw some of these symmetries and did them all together into 4 laws. And I wish you could see the equations for these, because beautiful equations. You wouldn't understand them necessarily. But let me just find them real quick. There are many ways of writing them, and it will look crazy to you used to the symbols. To see them. Yeah, I guess it won't really make sense. But anyway, so the equations are very beautiful, and they're very symmetric, and they have a lot of interesting relationships. So the first one, Gauss's law, talked about way near the beginning of the class, talked about the relationship between the electric field strength and charges. If you have more charges, then you'll have more electric fields. The second Maxwell's law is basically says that there's no magnetic charges. You may remember when we talked about magnetic fields, they had to be closed loops. There couldn't be any open magnetic field lines. That all magnetic field lines were closed loops. And there's no way that you can take a magnet and cut it into smaller pieces and end up with only a north pole or only a south pole. You always have both together. That's not true for charges. If you do this and you cut them down, eventually you can get to something that's a positive charge just by itself, or a negative charge just by itself. But in magnetism, you never get that. You always, even at the very smallest scale, even a single electron, a north and a south pole. Then you get some of these things that we have been talking about in this last couple of classes. Fields create magnetic fields. Field. You put all these together, and these are called Maxwell's equations. Everything in electricity and magnetism can be described starting with these equations. Everything. From how your computer works to how laws we've discussed, Ampere's law, Faraday's law, the Lorentz force, everything. It all comes back to these 4 laws. They are the fundamental law of electricity and magnetism, and they're really amazing. And when you do the full equations, you can find out what the speed of the waves should be. And the speed of the waves should be 1 over the square root of the permittivity of free space and the permeability of free space. So what do these mean? These were just constants in, for example, Coulomb's law, which said that the force between 2 charged particles 1 over 4 pi just 1 knot is Q1. Oh boy, sorry. Q2
over r squared.
So epsilon naught is related to the strength of the electric charges pushing each other around. And then, for example, there was a magnetic field. Mu naught we didn't talk about as much because it's related to magnetic field.
So, for example,
the magnetic field due to a wire is equal to the permeability of free space times the current flowing in that wire over, I think it's 2 pi times r. We said that the magnetic field was closest right next to, or strongest right next to the wire,
and got weaker further away.
And so mu naught so epsilon naught is basically how well do charges interact, and mu naught is how well do currents create magnetic fields, right? So if you were in another universe where mu naught was 100 times bigger than in our universe,
then you could create really strong magnetic fields with little current.
Okay, but these were just fundamental constants. You could take a current of a known amount and a known distance, measure the magnetic field strength in whatever units you wanted, and then determine what, this is a constant of the universe. It's just a property of what the universe is like. It has nothing to do with, it's not anything special other than that. And so Maxwell found that the speed of these electromagnetic waves was 1 over the square root of the product of these two. And so then he took these, he put them in the right units and figured out what it was. And he saw that the speed was 3 times 10 to the 8 meters per second. And this is the speed of light. So we'll come back to the fact that this is light in a minute. 3 times 10 to the 8 meters per second. Is that fast, slow, big, maybe not? We'll get into speed, light, and time travel. That's a separate thing.
But
that's a whole separate question. Here, I just want you to have this sense that the speed of light is easy fast, right? Like go all the way around the Earth 8 times a second fast. Look at this, 10 to the 8 meters. Right, so even the tiniest amount of time, even a fraction of a millisecond, and light has traveled across the Earth. It only takes light 8 minutes to get all the way down to the Earth. And the sun-Earth distance is in, so 8 minutes. To travel a distance in 8 minutes means you must be really, really fast. Okay, so this is a very fast speed, and it's the speed of light. Now, he didn't start by saying, okay, I'm going to figure out where light comes from. He started by saying, oh, I have these equations. Let's see what kinds of solution, let's see what kind of answers satisfy these equations. Oh, there's a wave version. Okay, fine. What is the speed of this wave? And then he found, and then he recognized. And before Maxwell, this is sort of like, there was no reason to suspect that light had any connection to or to magnetism. Light isn't affected by electricity, really. It's not affected by magnetism. It's not its own thing. So all of a sudden, Maxwell ties together electricity, magnetism, and light all. And this was a huge advance. This was an amazing. People had previously recognized what light was, and when he saw that it was due to this, he then postulated light and what you perceive as light is really electric and magnetic fields changing and exchanging themselves with each other, creating a magnetic wave. Okay, it really is quite astounding
what he discussed about
how light and electricity and magnetism are all basically sides of the same coin. They're